basically as efficient as a real reader, and it can now dump a full card in 0.7 seconds. Meep, meep. Going further towards an emulator on the card side, we still haven't completely figured out the 4-bit CRC, the transport CRC, but we can now deobfuscate our sniffed communications. This is actually the example I showed you earlier. Note, all these examples are synthetic. I'm not going to give you either the CRC or the obfuscation stream. In this example, you'll see that the first bit of the reader command is always the command code, and the other 8 bits are the address. That's address 0, 1, 2, and so on. And this is the actual response. You'll see that in this response, there's the UID byte and 4 bits of CRC. And you'll see that even for the same response byte, you have different CRCs. So there's something strange going on with CRC still. I at first thought that maybe the CRCs are chained, but it turns out that's not the case. Playing around, yeah, that's playing around with this. If you look at how a CRC is determined, it only has 4 input values. The register width, the polynom, the initial value, and the final XOR. And with any set of these 4 parameters, a CRC is uniquely determined. For a 4-bit CRC, it's easy, and for an 8-bit CRC, it's basically easy to just try out all the different ways for these 4 parameters and just set up a small Python script to try them all. And with this, I then found out how the CRC is calculated, how the initial value and the CRC polynom is, which I'm not going to tell you. And especially even more important, over which values the CRC is calculated. It turns out that the CRC that's sent by the card after the response by the card is calculated also by including the command bit and the address. So over this whole data, the CRC is calculated. That's why the different CRCs are for the same response byte on different addresses. Now that you have this, you can build a fully functioning emulator that can work with any reader and can spoof any card content. Especially you can spoof card content that you've read just previously with the reader I gave you. With this, I'm able to emulate. And yes, I've tried that. I've already opened at least 1 door with this emulator.
Remember that all the cards are the same, so this includes emulating master cards in the tree, not just user cards.
Actually, for myself, I wrote a nifty emulating program that will let you choose the card type that you want to emulate in the UID, and then emulates an empty card with that UID that you can write to with the regular Windows software. Or I can, as I'm going to tell you later, choose to emulate a master token of any type. For writing to cards, it's very similar. As it turns out, the write command that's being sent by the reader is either 21-bit or 23 bits for the different card types. It contains a command code, which, not surprisingly, is different from the command code for reading. It's 0. The address and the data, and then the CRC. The CRC calculation is essentially the same, but with a different command code. And the card will acknowledge with some acknowledgement. And after that, the data on the cards change. So now I can write to cards in that. Now, looking at the master token system control, which is a fun thing to say, we had, luckily, a demo set at our disposal for a very short amount of time. So we just made sniffs of a couple of different functionalities, like loading an IAM card into the reader and creating cards with that. Analyzing this the sniff of the load IAM command, you'll see that the UID and CRC are read, then some of the bytes at the beginning are read, and then 1 byte at the end is read. And similar, the read process of a SEM card, which is launching a reader, looks very similar, though for some reason they chose to make the launch process take really long. It's taking like 15 seconds. So there's an illusion of something very profound going on, like a very complex key derivation or hashing procedure or whatever. In reality, or at least on the radio channel, it's only reading 1 byte of the card over and over and over again. Maybe it's not actually a security feature or an illusion feature. Maybe it's just so that you can't launch a reader by accident. Who knows? If you have a complete sniff, you can reconstruct the token contents. This is an IAM card. Again, this is a synthetic example. You see the UID at the beginning. This is the UID, then there's a CRC, then there are 2 bytes that somehow seem to determine the token type, and this is the stamp of this master token which I created for myself. And at the end there's something that will turn out to be a CRC. I tried to copy this data with my writer to a physical card to just use that for my further experiments. Turned out that didn't work. The bytes that are lying directly after the UID, bytes 5 and 6, behave very strange when writing. When Googling around, I found exactly 1 information source about the Legic card format in Chinese. Translating back with Google Translate, I found that this is, or at least by this one author, is called the decremental field, and its contents can only be decremented. So this kind of makes sense when determining the token type for a master token. You will have to have a value in there that's greater than for a normal user card, so that you can turn a user card into a master token. But as Karsten said, we have a couple of empty cards here, and on the empty cards this byte is set to the maximum value FF, so we can turn these into master tokens.
Yeah, so this is the equivalent to fuses you have on smart card chips, where to distinguish different types of smart cards, you would blow some of them in the factory. So this is generally a good idea, only in this case they aren't blown in the factory. It's left up to the user to blow them. So there's no added protection through that whatsoever, unfortunately.
Yeah, also I wouldn't care about that at all. I still have my emulator, which just doesn't implement this feature, so you can write to any of these cards. I didn't mention that explicitly, but my emulator is of course fully writable. So I can write to that emulator also through the radio interface. The last byte, as I said, the byte 21, turned out to be a CRC, and as I said again, there are very few parameters to a CRC. By playing around with these parameters, I found a common set of parameters that works for both the UID CRC and the master token CRC. So now I can calculate the master token CRC and can of course create arbitrary master tokens with arbitrary contents. I just don't know yet what these contents would mean, which I'm going to play around with again. It turns out that byte 5 seems to control somehow the token type. Byte 6 somehow seems to affect the stamp length in coordination with byte 7. And for the cards that we saw in our short stint, the stamp length was 4, so byte 7 had 4 or 4 in there. The Windows software is kind of panicky, not very stable in this regard. If you have wrong values for some of these fields in there, it will just freak out and crash or exit or report confusing error messages and forgot that it has a reader connected, and any of these. For my first try, actually, I hadn't even reverse engineered the CRC at this point. I was just trying all the CRC values in order, or the 256 bytes. So I wanted to have meaningful values in these fields. I set byte 7 to 0, byte 6 to FC, then tried out all the CRCs, and turned out I got myself an IAM, but an IAM with a stamp length of 0. As you have heard before, for the stems or genetic code, it's a prefix match. So a stem length of 0 matches all prefixes. I now have